Good morning, everyone, and welcome to the webinar. My name is Rebecca Bailey, and I will be the moderator for today's webinar. We have a couple of housekeeping items before we start the webinar. First, we would like to let everyone know that Rosa is looking for potential webinar speakers. Specifically, we are inviting investigators who are early in their career and are doing interesting research in modeling and drug development to send an abstract and a short bio to webinar@rosaandco.com. And we'll be going through all of the submissions to find really great webinar speakers. If you're not an early career investigator, but do know someone who is and admire their work, please go ahead and send us a recommendation, and we'll invite them to send in an abstract. Our second item, our speaker will be taking questions at the end of the webinar today. You can submit your questions at any time during the webinar by entering them into the questions pane on your GoToWebinar side panel. I am particularly pleased to welcome today's speaker. Her work was featured on Rosa's Twitter page and was recommended for a webinar. And we are very pleased that she accepted our invitation to speak. Today's speaker is Natalie Morris. Natalie is a final year PhD student in Professor Sabine Hart's Swarm Engineering Group. Her project is based around computational and experimental approaches to the design and development of next-generation antivenoms. In addition to pharmacokinetic modeling, she has experience in building synthetic antibody libraries and ribosome displays. She holds a Bachelor of Science in Molecular Biology from the University of Sheffield. And I'd like everybody, please join me in giving a very warm welcome to Natalie Morris. Natalie?
Great, thank you. Yeah, thanks so much for the introduction, Rebecca. And yeah, thanks so much for the invite to speak. I'm really looking forward to kind of giving this talk to you all today. And yes, I'm Natalie. I'm literally just about to submit my thesis, just on the cusp of it, and I'm going to talk about work I've been doing over the past 2 years. So I'll just turn off my camera so I'm not distracted by a floating head and get started. And so yeah, the title of my talk is Defining Design Rules for Next Generation Snakebite Antivenoms. And as I said, I've been doing this for about the past 2 years. The first half of my project, I was basically making antibody libraries in the lab. But yeah, this has been sort of a focus of mine for the past 2 years. So what makes a pharmacodynamically effective antivenom? This is really the key question at the sort of heart of my talk and of my thesis. And so through this session today, I'm going to talk about the pathology of snakebite and how venom affects the body, current and next generation approaches to antivenom development, how I've actually built a model of envenomation and treatment, and then a computational framework that I've kind of implemented to optimize antivenom design. And then resulting from this, a couple of generalized guidelines that have come out of this model for effective antivenom design. So snakebite is a neglected tropical disease. I think it's often quite frequently overlooked, I guess, because it's non-communicable. But it's a really serious occupational and environmental health hazard for a lot of people around the world. Annually, there's about 2.7 million envenomings, which lead to over 100,000 deaths and a further 400,000 cases of disability. And these are really serious injuries, including amputations, blindness, permanent muscle contractures, post-traumatic stress disorder. And so this illness has a really serious kind of health and socio-economic burden on the affected individuals. And the burden is really overwhelmingly on developing countries. So this graph here on the right, it shows the number of deaths per region per year from snakebite. And so darker colours basically indicate more deaths. And what you'll see from this quite clearly is that the majority of the burden is focused around sub-Saharan Africa, South and Southeast Asia, and Central and South America. And what you'll kind of notice from this graph, and what I really want to highlight, is that Australia, so although Australia's got some of the most dangerous snakes in the world, it only actually suffers under 10 deaths per year from snakebite. And this is really testament to the fact that they've got a really good health service, they've got really good access, supply and provisioning of antivenoms, they have ambulances, you know, their road and transport infrastructures are really good. And the same kind of facilities are not necessarily afforded for a lot of people around the world, but it really does highlight the fact that actually most of these deaths are preventable. So snakebite causes a range of symptoms, and they can be broadly categorized into hemotoxic symptoms, neurotoxicity, and also cytotoxicity. So hemotoxic venoms will typically cause things like hemorrhage, blood clotting failure, and hypervolemic shock, which so your blood pressure drops to dangerously low levels. You can also get heart issues because of that. Neurotoxic venoms will typically cause neuromuscular paralysis, and they can also result in respiratory paralysis, where your diaphragm stops moving, so patients will stop breathing. And then we also have myotoxic symptoms, which include things like rhabdomyolysis, which is a generalized breakdown of muscle tissue, and also local tissue damage and necrosis, blistering, edema, and you know, depending on how that's kind of sort of managed, it can lead to things like gangrene and result in the requirement for debridement surgeries or limb amputations. So these symptoms are caused obviously by snake venom, and venom is a really fascinating substance. So it is a modified saliva, and it's about 95% protein by dry weight, and it kind of exerts its toxic effects through a really complex mixture of protein toxins. So in a given venom, there can be up to or over 100 different toxins, and there are over 30 distinct families of protein toxins which we know of in venoms. These toxins are often multifunctional. They can often act locally and or systemically. They're often highly synergistic and can amplify the effects of each other. They frequently present in multiple isoforms with varied structures. They're often heavily post-translationally modified. And so, as you can imagine, they span quite a wide molecular weight range, and it really ranges from very small peptides up to really large multi-subunit globular enzymes. And so the reason why we see such different kind of pathological symptoms between different types of venom is because snakes can vary quite substantially in their venom composition and the toxins that are in the venom and their relative abundances. There's also actually there can be a lot of variation in venoms of the same species on geographic basis, on the basis of snake age, sex, diet. And so all of this gives rise to the really diverse pathophysiological and also pharmacokinetic properties that different venoms have got. So there's over 200 species of medically important venomous snakes, and most fall into two major families, the elapids and the vipers. So the elapids are typically more neurotoxic. They contain generally more low molecular weight toxins, and their venom generally more rapidly absorbs and distributes through the body. So some of these snakes, the ones that are really lethal, they've actually been known to sort of kill patients within an hour, because the venom can just get into the body that quick and distributes that quick to obviously its sites of action. The vipers, conversely, they're typically more hemotoxic and cytotoxic in their pathology. So they have more high molecular weight toxins, things like big metalloproteinases and serine proteases. And these venoms tend to absorb more slowly and persist for longer. With viper envenomation, we can see things like recurrent envenomation, which is where you can treat a patient with antivenom, and because venom can still be leaching from the bite site over a prolonged period, patients can actually see a recurrence of the envenomation symptoms. So these two families have got like broadly distinct like pharmacokinetic properties in general to their venoms. So we currently make antivenoms from the sera of hyper-immunized animals, and the way that we produce antivenoms hasn't really changed that much in about the past 50 or so years. So the way we do this is we immunize large animals like horses or sheep with controlled doses of venom from either one or several snake species. The horse will then develop an immune response to the toxins and start producing neutralising antibodies against the lethal components of that venom. And then after a prolonged period, so at least a year, we can extract the serum, and then we can precipitate out the IgG antibodies, and we can potentially also use pepsin or papain cleavage to get Fab2 or Fab fragments, which will have different pharmacokinetic and also immunogenic properties because they're different sizes and they don't have the FC region of the IgG. So these antivenoms, they are effective at preventing lethality, and like if you ever bitten by a snake, you definitely will want one of these serum antivenoms, but there are numerous limitations to the way that we currently produce them, just inherent to the fact that it is essentially serotherapy. So these include, so obviously the processing requires animal husbandry, it requires caring for horses and snakes, which kind of drives up the cost. The geographic variability of venomous snake species means that generally like the scale up of these kind of productions is quite difficult, which drives up the cost as well. They also can often have quite low therapeutic potency, and so it's quite expensive to actually purify out the toxin binding antibodies from these antivenom mixtures. And so studies have looked kind of at the amounts of neutralising antibodies within antivenoms, and in some formulations it can be as low as 5 to 10%. And so the rest of that, we're basically giving patients large amounts of kind of non-specific horse antibodies against like horse flu and like other kind of sort of antigens which the horse has been exposed to. And so this means that these therapies have got quite a high risk of adverse effects. Things like serum sickness, anaphylactic shock are fairly common. And this also means that because the potency is lower, it drives up the dosing requirements and also in turn the cost. So the cost of the antivenom, it can vary a lot. So in the cases where like there are polyvalent formulations which are very like broadly specific and maybe they're being produced by bigger sort of government organizations, they can be cheaper. But say for example in like sub-Saharan Africa, like the typical cost of a vial of antivenom is over $100, and patients can require like up to even over 10 vials for treatment depending on like what snake they've been bitten by, how much they've been envenomed by. So you know, for the poorest people in the world who are unfortunately often most affected by this, it can be quite an expensive treatment. And the last point as well is obviously there's quite a lot of batch-to-batch variability just because it's an animal production method, and they're also frequently quite ineffective against necrosis, which is kind of just a combination of the fact that necrosis can set in quite quickly, and also some of these fragments sometimes can like struggle to reach the site of the bite following an intravenous administration. So because of all these kind of like limitations and sort of inherent difficulties with this serotherapy, there's been a lot of research that's been done in recent years to improve the way that we make antivenoms. And people are kind of following lots of different sort of research avenues, and these include things like targeted immunization strategies, and also looking at repurposing like small molecule drugs. But one sort of aspect of this that I'm really interested in is the development of next generation recombinant antivenoms. And this is because my experimental work was all kind of similarly based around sort of synthetic antibody library design. So in this kind of a workflow, essentially you would use an in vitro selection method such as phage display or ribosome display. And you can basically use this to screen a library of hypervariable antibodies or some other binding protein scaffold against a toxin target of interest. And then basically these methods, they've always got a way that you can actually get back the DNA from those effective binders. And then we can express those high affinity binders in a cellular culture, in like bacterial culture or eukaryotic culture, depending on the type of scaffold. And then that will basically give us a pool of targeted binders against specific toxins. So this is a way that we could potentially really improve the safety and the efficacy of these antivenom therapeutics. And also cost predictions have projected that we expect that these kinds of formulations could be on a comparable cost level or a little bit cheaper than current serum antivenom formulations. So and there's additionally kind of a range of antibody engineering approaches which are really kind of expanding this design space for antivenoms. So in vitro selection, the key benefit of it is that you're not kind of constrained to an animal's immune system, and so you can potentially use alternative scaffolds. So these are things like DARPins, antibodies, adnectins. There's a whole host of alternative scaffolds which are kind of alternative, really, really stable proteins that we can kind of graft like binding loops onto. And these alternative scaffolds might have really advantageous manufacturing or immunogenic or pharmacokinetic properties for antivenom production. So we're no longer really bound by conventional scaffold types. There's also antibody humanization, which can basically make the the treatments better tolerated by the body. Affinity maturation, so we can improve the affinity of these fragments in the lab. And there are also ways that you can kind of modify the affinity maturation experiments to either evolve K on or K off preferentially. And there's also more general structural engineering approaches where we can look at modifying things like valency, size, and half-life through more classical kind of protein engineering of like grafting on different sort of domains. So because of all this, we can now produce antivenoms with really diverse PK/PD properties. So on the top here, I've just got a couple of examples. There's some toxins, which you can find in venoms, which I've just grabbed from the protein data bank. And you can see that they're spanning a size range here of about 150 kilodaltons down to 6 kilodaltons. And similarly, the antivenom scaffolds that I've put here, so the 3 conventional scaffolds, IgGs, Fab2s, and Fabs, and a couple of next generation scaffolds, which are currently under research, small chain variable fragments and nanobody fragments. These span also quite a similar sort of size range. And so, they also have similarly diverse PK properties, whereby smaller scaffolds typically exhibit increased elimination and increased tissue perfusion. And so kind of the key aim of my modelling is to kind of understand how this choice of antivenom format will affect the treatment outcome. And specifically looking at if certain scaffolds are better suited at treating different types of venoms, primarily the elapids versus the vipers, and also if certain scaffolds are preferable under particular envenomation scenarios. So in this work, I've simulated 2 model venoms. So my model elapid venom was from the equatorial spitting cobra. And this is a low molecular weight venom with an average toxin size of about 9 kilodaltons. It's neurotoxic, it rapidly and very extensively distributes, and I think it's a World Health Organization category 1 listed snake. I think it's one of the more medically important ones listed by WHO. And then for the viper venom, I used the parameters for the mangrove pit viper. So this is a much higher molecular weight venom with an average size of 57 kilodaltons. It's hemotoxic and it distributes more slowly with a longer half-life. And yeah, these are basically 2 well-characterized venoms, which we've already got some parameters in the literature. So in my approach, I basically use compartmental modeling. So in this method, we basically split the body into a central compartment of blood and well-perfused tissues and a peripheral compartment of less well-perfused tissues. And there's some kind of benefits to this. So we get a description of bulk system dynamics. We get some degree of localization, whereby we can see what's going on in the tissue, which can potentially sort of correlate to some of the pathological effects that we might be seeing. So you get a bit more granularity than if you were just looking at the blood. And also looking at the systemics, we get a general indication of the lethality of the venom and the overall patient treatment. But really importantly, we can parameterize this using existing venom and antivenom data. So I did do a literature review of kind of venom and antivenom studies, and kind of the majority of the studies tended to report non-compartmental or compartmental parameters. So we kind of went with the compartmental system just for that extra degree of granularity. And in addition to this, it's also just quite a simple and computationally efficient modeling approach. So there's fewer parameters than if I was trying to build a really complex PBPK model, which means that there's a bit less uncertainty around the parameterization potentially. And also the computational speed of it means that I can actually implement brute force parameter optimization. And as you'll see through this talk, this has kind of enabled me to map the kind of optimized antivenom parameter space to quite a nice degree of resolution. And it enables me to get optimized parameter ranges as opposed to just specific combinations, which you might get with a more like classical machine learning optimization approach. So as I mentioned, the model is a 2-compartment model. So and it's quite intuitive. So basically at time 0, we've got an intramuscular bite site. Venom is injected from this bite site into the central compartment with a limited bioavailability at a absorption rate of Ka. After a time delay, we inject our antivenom intravenously as a single bolus dose. Venom and antivenom can circulate through both compartments via intercompartmental transfer rates. We account for binding with a rate of K on and spontaneous dissociation with a rate of K off. And all of these species are eliminated through the central compartment at a rate of K10. And it's not marked on here, but the neutralised complexes can also transfer between compartments. So I originally wrote the model with just monovalent binding, but we've recently expanded it to also incorporate bivalent toxin binding, so we can also look at the effects of multivalent scaffolds. So how we parameterize the model. So as I mentioned previously, we used experimental data to parameterize it. So I did a big literature review of venom and antivenom studies in as many species as I could find. So it ranges from mice up to humans. And I chose the rabbits to parameterize it just because the rabbit has been most frequently used in the literature for both venom and antivenom studies. So the venom parameters were taken directly from the literature, but I needed a way basically to predict how particles would move based on size, because that would enable me to simulate antivenoms of quite variable sizes and also simulate neutralized venom-antivenom complexes. So in order to do this, I did a series of quite simple regressions where I'm basically taking these parameters from different antivenoms and also a couple of low molecular weight toxins up at the lower end here, just to get kind of an indication of how these particles have moved based on size. So none of these data points were from studies that exhibited any like target mediated drug disposition. They all exhibit just your regular like compartmental distribution and elimination kinetics. But yeah, it's basically just the way that we're plugging in like actual data for how these particles, we expect them to move in a rabbit. So this here shows predicted dynamics for some model antivenoms. So this is using the K10, K12, and K21 parameter predictions based on molecular size from the regressions on the previous slide. So if we just look at like panel A, this here just shows the IgG, which is our biggest fragment. The solid line is the central compartment, the dotted line is the peripheral compartment, and we can basically see that this fragment here, it's got a much longer half-life and it doesn't really actually perfuse that much into the tissue, which is what we'd expect. And then as we go down the panels, we're reducing in the size of the fragment, so that by the time we're at the nanobody here, it's much smaller than the IgG. It's got a shorter half-life and it's much more tissue diffusive. So yeah, the IgG Fab2s and Fabs, their central compartment bloodlines, they're kind of in keeping with the bounds of kind of literature review studies that I was able to find for these fragments in rabbits. For the alternative scaffolds, small chain variable fragments and antibodies, it's a little bit more unclear just because they've not been really as sort of, these antivenom fragments haven't been as well characterized in rabbits yet. But it does still follow the general trend of sort of increasing tissue perfusion, decreasing half-life with decreasing size. And also we can basically say that this scaffold here, it really is like a placeholder for a binder, which is going to move in a very similar fashion to the small toxins, which is essentially the whole logic really for using these smaller nanobody scaffolds. So this here is just showing some example model outputs and really just to kind of show that we've got a lot of control over different parameters of interest. So on the left, we've got the central compartment concentration time curves. On the right, we've got the peripheral compartment. And so in this case here, we're injecting 3 milligrams of the elapid venom. The venom's shown in orange. We're treating at 4 hours with a monovalent nanobody antivenom. So the antivenom is shown in blue. And we're treating with a 1:3 dosing ratio of venom to antivenom particles, and the affinity, we can separately set the K on and the K off, and it gives a total KD of about 1 nanomolar. And so this treatment here is really strongly neutralizing in both compartments. And yeah, we've basically got control over all these different parameters, which is really good for kind of testing how different antivenoms will perform in different circumstances. So one of the things we looked at was variability in envenomation scenarios, because field bites, there's loads and loads of different sort of factors which can affect really a patient's envenomation course. One of them is actually the amount of venom which is injected. So snakes can inject very variable amounts of venom. Sometimes they can bite and they don't even inject any venom at all. And so this is a big kind of like unknown when patients come into the clinic. And so what we wanted to test here was how a static dose of antivenom would treat a variable dose of venom. So here we're applying a venom dose of 0.25 to 5 mg per kilo, and we're treating it with a static dose of 2.5 mg per kilo Fab2 antivenom. And so the clouds basically indicate kind of the upper and lower bounds for each of these species that you would see across this venom dosing range. And so we can see from this, the central compartment, this antivenom dose is quite effective actually at clearing all of the venom in the central compartment across these ranges. But in the peripheral compartment, if a patient was to come in and had been injected with this higher venom dose, you wouldn't get a particularly good neutralization necessarily at those higher sort of levels. We also looked at the effect of variability to absorption and bioavailability. So snakes can bite in different locations on the body and to different depths. So elapids typically have shorter fang lengths, which tend to result in more subcutaneous injections. And vipers tend to have longer fangs, which typically lead to more like intramuscular injections. So this will all affect kind of absorption patterns. So in this scenario here, we apply a static venom dose. We also apply a static antivenom dose, but we're varying the bioavailability 50% above and below baseline, and we're also varying the absorption rate. So the baseline absorption rate for this venom, it gives a Tmax of 1 hour, and here we kind of alter the absorption so we can span between 0.5 to 3 hours. And kind of the clouds here are basically looking at the combinatorial effect of these two parameters as they're varied together. And it basically gives you sort of, again, like upper and lower predictions. And we can see that like the variability is really mostly focused on how the patient is before they're treated and how they're going to present in the clinic. And at the point of treatment, actually, this dose of antivenom is quite good at sort of neutralising that venom which has been applied. So kind of the next part of my work was to really use this model to do some optimization simulations. So kind of really wanted to sort of look at how you can apply sort of an engineering sort of logic design build test cycle to it really. So in this you obviously have your experimental venom and antivenom parameters. In the optimization simulations, I consider variability to both 5 antivenom design parameters and also some treatment scenario parameters. We then run the PK modeling for each of these different conditions, calculate a treatment outcome metric, and then use that to identify the best treatment. And then hypothetically in the future, we could design and test these optimized treatments, which would then provide additional data for the model in a kind of positive feedback loop. So in terms of treatment metrics, I looked at 3 different metrics that we could use to indicate damage. So all of these metrics are calculated on the venom curve, and they're all calculated from the point that antivenom is administered up until the end of the simulation. And so the first one is the area under the curve, which just indicates obviously the exposure of the body compartment to the venom. The second is the time over the threshold. So this is going to be the time that it takes an antivenom to bring a venom level below a critical threshold. Well, we're basically defining this critical threshold as, you know, it's basically like a concentration that we're thinking is going to result in kind of quite clinically significant systemic symptoms. So this is going to indicate, I guess, the speed of neutralisation. And we also looked at the AUC over threshold, which is kind of a combination where we basically take the AUC over that threshold. And I kind of looked at these methods, compared them, and for my study, I basically applied the AUC over threshold to the peripheral compartment. So it has a few benefits. We consider concentration as well as time. It also will exclude any negligible persisting levels of venom, because obviously ODE simulations, they often resolve to a steady state. And if you're, for example, resolving to a final concentration of like 2 nanograms per mil or something really low, it's unlikely to be really having a clinical effect. And we apply it to the peripheral compartment just because the kind of delay, the compartmental transfer dynamics that we see basically mean that you get like a wider sort of dynamic range of behavior in the peripheral compartment versus if you calculate it in the central compartment, where antivenom is immediately administered to that kind of homogeneous sort of well-mixed compartmental space. And so because of this peripheral compartment metric is a bit better in terms of sort of like comparing treatments, and we can gauge more information on it from a comparison point of view. And so the threshold, we looked at different clinical envenoming studies from related snakes, and we use a threshold of about 50 nanograms per mil. It's very much a ballpark value, but we could change this in the future kind of with more information if we needed to. So the antivenom parameter, for the antivenom parameter set, I basically made a set of 200,000 theoretical antivenoms, which varied across 5 dimensions. So we looked at scaffolds ranging in size from 15 to 150 kilodaltons, so a nanobody up to an IgG. Valency, we looked at scaffolds that can bind either 1 or 2 toxins per antivenom. We looked at a K-on range of 10 to the 3 to 10 to the 6, and K-off of 10 to the -6 to 10 to the -3. And so basically these K-on K-off combinations give us a KD affinity range of, I think it's about 1 or maybe 10 micromolars up to into the picomolar range. So it kind of gives a range of like suboptimal affinity up to really, really strong affinity, which you'd really probably have to get through affinity maturation tests. We didn't go any lower with these K-on and K-off lower bounds, just because if we went much lower, you actually just end up introducing lots of really completely ineffective scaffolds to the optimization. So we set the kind of lower level at that sort of area there. And then for the dosing, we also varied the ratio of venom to antivenom particles from 1 to 1 to 1 to 10. So we use a ceiling of 10 because so in the literature, there have been cases where people have used dosing ratios of 1 to the 6 for venom to IgG antivenom particles in sort of mouse studies. And we also anticipated anyway that like the smaller scaffolds would probably require a higher baseline dose. So we thought we'd just kind of like push that dosing level up a bit. But also I think in the future, hopefully if we get more information on kind of toxicity limits, we'd also be able to refine this a bit further. So we also varied some treatment scenario parameters. We're comparing elapid and viper venoms. We simulated treatment times ranging hourly from 1 to 10 hours post-bite, and we basically ran those 200,000 antivenoms at each time point. So it gives us a total of 2 million simulations per snake, which I then did parameter optimization and global sensitivity analysis on. So this is my first result slide. So these are basically what I'm calling the universal scaffolds. These are the antivenoms which result in the lowest 1% AUC/OT scores at every single time point. So at treatment times of 1 hour up to 10 hours, these scaffolds are in the top 1% of all scaffolds. And on the left, we've got the elapid results, and on the right, we've got the viper results, and I've split it into monovalent and bivalent antivenoms. And basically what you see from this is that there's a generally like these scaffolds tend to be high affinity, high dose, but we see that for both snakes, it's quite tolerant of a wide molecular weight range, and it's also quite tolerant of these different valency configurations. But we do see like there's a big difference between the elapid and the viper in that there's a narrow region of parameter space that works for the viper bite, and there's more stringent design constraints really for this envenomation case. So this slide here is basically showing the same scaffolds, but as a kernel density estimation. So on the left, we've got the elapid, the right, we've got the viper. I've basically put all the monovalent and bivalent scaffolds together here. And essentially, this is like a contour plot. So darker regions will basically indicate that you've got more solutions in that area of parameter space. And so it really is going to start to kind of indicate if there's any like preference for specific types of scaffold. And what we can basically see that for both snakes is that there's a definite preference for smaller scaffolds at high doses. And on the affinity panels on the bottom here, we can see that there's quite a strong preference for high K-on, more so than there is for the K-off. So the K-off solutions can span actually quite a wide range across these orders of magnitude. But yeah, the K-on is very much more kind of like 10 to the 5 and above predominantly. So we also looked at poorly performing antivenoms. So these are the antivenoms which perform with the highest 50% AUC/OT scores at every treatment time point. And when we look at the density here, we can basically see these scaffolds tend to be quite low dose, so 1 to 1 to 1 to 2. And again, they can span quite a wide molecular size range, really across the entire sort of parameter space that we've got. And in terms of affinity, it very clearly does not overlap with what we saw on the previous slide, in that this is quite clearly, it seems to tend to be scaffolds with the lower K-on values in the order of 10 to 3 to 10 to the 4 for both snakes. And again, we can see there's quite sort of a wide K-off range, which can go along with these poorly performing scaffolds. So this here is looking at like time-dependent variations. So we're looking here at the viper scaffolds with the best performing viper scaffolds, which are performing in the lowest 1% of AUC/OT at different treatment time delays. So in the top panels here, we're showing when we're treating at 1 hour, and at the bottom, we're showing when we're treating at 6 hours. And so when you look here on the left side, molecular size against dose, with increasing time delays, we see that there's basically an increasing preference for smaller scaffolds and for high dosing. And then we can also see that on the affinity panels, with increasing time delays, there's an increasing preference for a high K-on. So it's actually quite interesting. If you look at the K-on distributions for the best performing scaffolds across the treatment times, we actually see that the distribution switches from being left skewed to right skewed. And so what I did was I pulled out basically the mode of these, the mode of the K-ons of the best performing scaffolds, and it's plotted here on the right. And you can see that actually, if you're treating early at like 1 hour, the most frequent K-on is actually more in the order of 10 to the 4. And then beyond that, it kind of increases and plateaus up to more like 10 to the 5 to 10 to the 6. So I thought it was quite interesting, just the fact that it's not static and all the time, you know, at that upper ceiling. There is some kind of dynamic behavior sort of that we can see here. And so this here is plotting the most effective scaffolds as violin plots. So these are the universal scaffolds that perform the best at every treatment time. And these are essentially like smoothed out histograms, and they show basically the molecular size distribution of the scaffolds. And I've also separated it by valency. I've done this just so that you can then start to kind of mark on some scaffolds that we know that we can potentially develop and where they would fit along this like distribution of optimized solutions. So what you can see from these plots is quite clearly that kind of it tends to be the smaller scaffolds which are sort of the best performers for both snake venoms, typically in the range of 20 to about 30 kilodaltons. And this really indicates that we're getting more effective solutions around this kind of size range, and that essentially that the design parameters around these scaffolds for the other parameters, like for example dosing and affinity, are probably a bit less stringent than if you're using like a larger scaffold. So yeah, we find more effective scaffold solution at these lower sizes. And so kind of the last analysis I did for this was a global sensitivity analysis. So I implemented the PAWN method, which is a density-based GSA method. And I use this because it's good for highly skewed or multimodal outputs. So this here just shows an example output of one of my 200,000 antivenom simulations for the elapsed 3 hours. And as you can see, it was really right skewed. And this is a trend that I saw across all the simulations. Basically, if you use a variance-based method for outputs like this, it can add some like inaccuracy to your kind of parameter, your influence estimation. So kind of the aim of this sensitivity analysis is obviously just to ask which design parameters are influencing the treatment outcome the most, and therefore, you know, if people are designing antivenoms, what kind of factors should we focus on the most? And it gives us sensitivity indices, which again indicate the influence of a parameter on a model output, where a bigger index means that the parameter is having a bigger effect. So this here shows the plots. So you'll see on the key on the right that there's a dummy parameter. This basically sets the threshold of influence. So anything that is kind of at or below that level, we basically can't really conclude that it is having a significant impact on the model's output. But anything above that, we can say it's having an influential impact. And obviously anything that's higher, it's having a relatively larger effect. So I basically repeated the sensitivity analysis for all of the separate treatment time points, so I could look at how the sensitivity was changing with early and delayed treatment times. And to start, I just looked at the full output distribution. So for each of these treatment time points, I'm running the sensitivity analysis on all 200,000 of those theoretical antivenom simulations. And from these, we can see that the elapid and the viper profiles are very similar, and that K-on is overwhelmingly the most important factor, which is kind of what we'd expect from what we've seen in the optimization studies. And the other factors have kind of got much lower and kind of like overlapping sensitivity profiles. But kind of the interesting thing about the PAWN method is that it's not dependent on the shape of the input parameter sample at all. So this is really useful because it means that you can basically run a load of Monte Carlo simulations, and then you can basically look at the distribution. You can say, I want to look specifically at the sensitivity of outputs at the head of that distribution or at the tail. So you can start to look at kind of the extreme effects and any kind of differences in those kinds of model outputs. So that's what I did. I basically set a threshold of 300 as my AUCOT score, which is basically just serves as like a static threshold. So anything lower than this, we're deeming it as an antivenom, which is having some like good or a really good therapeutic effects. And anything with an AUCOT score of bigger than 300, we're deeming it as less effective or even ineffective. And so when we rerun the GSA simulations on the slice distributions, it's actually a little different. So panel C and D, this shows the result at the head of the distribution. So we see, first of all, there's more time-dependent variation, but otherwise it's relatively similar to the full distribution, with K-on as the most important factor. We'd expect this just because it is so right skewed, but dose definitely does come out as being more important when you slice a distribution in this way. But panels E and F show what happens when we look at the tail of the distribution with antivenoms which are scoring in those higher AUCOT scores. And in these cases, actually K-off becomes the most important parameter, followed by K-on, followed by dose. So I thought this was just quite an interesting kind of like nuance of the system, in that and it can be sort of informative to people who are kind of running these simulations, because there are ways to sort of modify your in vitro selection or affinity maturation experiments to preferentially evolve either K on or K off. And so it can kind of give some kind of guidance as to what is the more important kind of element of that sort of affinity binding reaction to sort of like focus on for improving your binding candidate. So based on this, I've kind of come up with some fairly basic sort of like guidelines for effective antivenom design. The first one is just that optimized antivenoms can span a really wide area of design space, which is ultimately a really good thing. We use quite a stringent sort of effective antivenom cutoff of top 1%. In reality, you could probably go lower than this, which is going to give you more kind of it's going to kind of relax, for example, the dependencies on dose and things like that. So the second guideline is that treatment is primarily mediated by affinity, specifically K on, but K off seems to have quite a big effect on more poorly performing scaffolds. And we basically also see from local sensitivity tests that you don't really seem to get much additional benefit from reducing K off below the natural sort of ceiling of 10 to the -4. So we also found that size has quite a minimal direct impact, and smaller scaffolds can be more flexibly designed, particularly for late treatment scenarios. High doses are better. Smaller scaffolds will outperform larger scaffolds when they're dosed efficiently, but you do have to give them like a higher baseline dose to kind of get them to that sort of performance level, just because they are cleared that much faster. And we also found that the Viper and elapid system seem to be optimally treated by the same types of scaffold, but the Viper parameter constraints just seem to be much tighter. And so in terms of like scaffolds which could potentially meet these requirements for optimized design, it would be things like bivalent nanobodies or monovalent small chain variable fragments. We'd be looking at kaons of at least 10 to the 5 and k-offs of kind of at least 10 to the -4. And kind of the dosing, the model suggests that the dosing would vary depending on if you're looking at the Viper or elapid case. I'll just quickly also talk about kind of future directions. So there's a huge amount of ways that kind of this modeling work could be expanded. So one way is kind of parallel simulation. So we've obviously only really considered the venom and the antivenom as like a homogeneous unit, but obviously that's really a simplification of venom definitely in real life. So there was a great paper came out a couple of years ago that was looking at simulating subpopulations of venoms just in an envenomation scenario, and I think potentially using similar techniques to simulate the treatment of a kind of subpopulations of toxins would be quite interesting to look at. And there's also the possibility of looking at cocktail antivenoms. So it's been suggested that we could make recombinant antivenoms using multiple different types of scaffolds, for example, nanobodies and IgGs, and that in itself is a whole other optimization problem in terms of scaffold stoichiometry and dosing, where these kinds of simulation techniques could be really, really useful. There's also the option to kind of add in more sort of mechanistic descriptors, so things like envenomation, pathway markers, maybe adding sort of additional body compartments to take it more in a sort of like PBPK kind of approach, and that could sort of enable these kinds of models to be interfaced more readily with like preclinical efficacy testing. This is obviously really important because venom research is quite, as you can imagine, it's sort of quite heavy on like animal usage, and so I think hopefully in the future kind of there'll be a greater uptake of these simulation methods that can reduce the amount that we do have to sort of use mice in kind of preclinical efficacy testing. There's also the potential to do spatialized simulation. So I think this is a really, really interesting thing that we could potentially look at, particularly for things like tissue necrosis. We didn't really look too much at the spatialization, but I think there's definitely, you could potentially add it in as additional compartments and take a multi-scale approach. It'd be really cool to kind of then get a holistic view of both local and systemic envenomation effects. Potentially there's other diseases that we need to treat using kind of antivenom cocktails that these kinds of approaches could be used for, and also kind of more like high level, but there's potential, say, for automated design. So I think artificial intelligence is obviously coming on leaps and bounds, and I also think that kind of the kind of issue of trying to make next generation broadly neutralising antivenom therapeutics against potentially diverse venom types, this really is an optimization problem, and it's the kind of thing that, you know, AI could potentially really, really help in and sort of improve the way that we are designing these sort of next generation treatments. So just to brief sum up, venom and antivenom pharmacodynamics is really complex. We've built a model of snake envenomation and treatment, and it enables use and control of a range of different antivenom and venom parameters. And yeah, basically established a framework through which we can start to optimize antivenom design. And this has kind of shown that affinity is key, and while molecular size doesn't seem to have a huge direct impact on the treatment outcome, smaller scaffolds seem to allow for more flexible treatment, particularly in sort of early and late treatment cases. And these kinds of scaffolds are definitely really worth a lot sort of more research on their kind of sort of PK/PD properties, and particularly compared to the more conventional treatments. So yeah, thank you so much everybody for listening. I'd like to thank my supervisors and my co-authors, Sabine Howard and Joanna Blee, and all members of my lab group. Yeah, I'll obviously take questions now, but yeah, if you've also got any questions after this, you can feel free to contact me via that email. And yeah, all my code is written in Python. It's all freely available by these publications, which I've linked below. The one on the left is a paper that we put out last year, which is about how the model was developed and all the equations and everything. And the one on the right is a preprint that will hopefully get through peer review and published very soon, and that covers all of the kind of global parameter optimization and sensitivity analysis work that I've recently done and spoke about here. But yeah, that's everything. Thank you so much.
Thank you, Natalie, for a very interesting webinar. We do have a few questions. I'm going to start with the first, which I think if the snake venom contains a complex mixture of toxins, do you have to screen for multiple targets, and you have to create a polyclonal antibody mix like the classic antiserum to prevent the several symptoms of each snake bite?
Yeah, so it's a really good question. So it's basically going to depend on the type of snake venom. So there's a paper came out quite recently where a group in Denmark, they found a single monoclonal antibody that was able to neutralize the lethality caused by a neurotoxic venom. But I think that was really because that venom's got lots of very, very similar neurotoxins. So you basically would need to target the different lethal components, but because there's often a lot of kind of structural similarity between these toxins, you can make polyspecific antibodies, which could then have more of a broader sort of like neutralizing effect. So there was a paper I read a while ago that they kind of predicted that for kind of like a polyvalent antibody mix to neutralize potentially like several sort of snake species, you might need up to like 10 different antibodies. But this is also going to be like an optimization problem, I think, in an area where maybe like AI could help in the future in terms of like selecting what are like the targets with like enough structural similarity that you can then get polyspecific antibodies. But yeah, like for recombinant formulations, you'd probably would be looking at like multiple toxins to kind of get the best sort of like therapeutic coverage, and it would be a polyvalent mixture.
You didn't include target-mediated drug disposition in your modeling. Was there a reason for that? And is there no target-mediated drug disposition in the PK of antivenom?
Yeah, so in all of the studies I looked at for both venoms and antivenoms, none of them reported target-mediated drug disposition, which I guess I was a little bit surprised about, particularly for the toxins. But yeah, it was all just reported as just like regular two-compartment dynamics. So yeah, that was basically why we didn't include it. I think though, yeah, if it was to go to a more like heavily decomposed model where you're looking at more like specific toxins, like specific neurotoxins or specific myotoxins or something, you probably would need to then put more of that spatial elements in. But yeah, just as this kind of initial model, we've basically just worked with what the literature has said, basically, because I haven't done any kind of experimental PK characterization for this. And yeah, it's just the papers that are out there basically don't report it, so we've not included it for this sort of model.
So you mentioned that your model was based on rabbits. Have you looked at modifying this to be more of a human PK PD model?
So it's a good question. So yeah, I collected studies from a range of different species. Obviously used rabbits because they were the most regularly quoted, and I did look at options for transferring it into humans. It's quite difficult just because if you're doing like allometric scaling, from when I originally looked into this, most of the kind of like allometric scaling constants that are reported in the literature, it's for things like clearance and like bonds of distribution, not so much for the rate parameters. So it was quite unclear, and different papers were using kind of different scaling exponents to do that. So I was a little bit, it didn't really seem like it was something, I basically wasn't sure if I was going to do that scaling that I would get something out that was really very reasonable. And there's the other point about this is just that while there are values for toxins in humans, there's inherent limitations to those clinical envenoming trials, just because patients often come to the clinic potentially hours after they've been bitten. And so if blood monitoring starts, say, 6 hours after a patient's been envenomed, you're going to miss that initial absorption peak and that distribution part of your PK profile. And so when you actually look at the pharmacokinetics of venoms in humans, they very, very commonly are reported as showing one compartment dynamics, just because you're just getting that elimination phase. Conversely, if you look at animals, they typically all tend to really say 2 or 3 compartments, mostly 2 compartments. And so that's why we've kept it as a kind of the rabbit study for this. I think we basically just need more data. Another way kind of around that would be if you could basically just use similar protein molecules in humans and use those as kind of analogs. But yeah, ideally in the future, we would move it into kind of a human system to be sort of more informative. But yeah.
So there are several questions on this next topic, so I'm going to combine them up. For therapeutic proteins, the canonical method would be physiologically based PK modeling rather than compartmental. And given the wide variety and location of effect sites that you've mentioned earlier in your talk, is there a reason why you didn't use more of a PBPK model here, or would this be something that would be done in the future?
Yeah, so I think it would be something that'd probably be done in the future, because yeah, I've not done any kind of experimental like PK characterization work for this. So we're just purely trying to go with numbers which were already available in the literature for these toxins and venoms, and they are definitely on the toxin side, pretty much purely kind of on this compartmental or mostly even at the non-compartmental level. So then there are probably ways that we could start to like estimate these tissue partition coefficients and stuff for a PBPK model. But as far as I'm aware, it can be a bit more uncertain when you're talking about like proteins and like drugs and like protein biologics, and I imagine also for toxins. So yeah, ideally in the future, it would move to a more like decomposed method, because I think that would give you even more granularity. But it was really just based on kind of data that was already available about how these molecules are moving, considering that we haven't really had access to do kind of proper sort of experimental like setups for this kind of stuff.
So you mentioned looking at everything from an IgG antibody through to nanobodies. If you had to select one size for what size would be an ideal, and could you basically give us a why?
Yeah, so the model basically suggests that you'd want something small, so in the range of 20 to 30, probably I think on the higher end of that is probably better, so maybe about like 30 kilodaltons. I think multivalency is really good, so I do think that things like the multivalent nanobody constructs is something that are potentially like a really, really good option for this. There have been some studies which have made bivalent nanobodies for toxin neutralisation, and even larger multivalent constructs where they've got like 4 or 5 different nanobodies in like a single toxin binding unit. So you get a nice degree of like modularity with that. And yeah, kind of, I just think as well that in terms of like these smaller scaffolds, you get a lot of benefits in that, even beyond like the PK/PD factors, and that you can produce things like nanobodies in bacteria, so it's a lot cheaper. And also the fact that it's so much smaller, it's going to reduce your absolute dose levels an awful lot. You do have to dose them higher to start with, just to make sure that kind of it's persisting in the body for longer. But yeah, from what the model suggests, it seems to be that like these smaller scaffolds are a bit better. But I would also say like that, you know, the experimental comparisons of different scaffolds that have been done so far, they have just focused on these conventional scaffolds, fabs up to IgGs. There's not really been any work thus far that I know of that has included these smaller alternative scaffolds. So I think it will still, I think, have to wait and see kind of what those kinds of comparative studies sort of say. But yeah.
So when you did this work, did you include a PK model of an existing antivenom?
Yeah. So So when we basically we validated the kind of the antivenom predictions using the studies that we got from the literature of the conventional antivenoms, so the IgGs, Fab2s, and Fabs, and we compared the blood serum levels from those drugs with our predictive central compartment blood levels. So we tried to incorporate that, and yeah, for the data for the parameter regressions, it largely includes actual antivenoms, basically, and how they're moving in rabbits.
And so when you looked at your PK predictions, did you include some of the uncertainties in the antivenom in the optimization simulations?
So with the regressions that we did, they're obviously kind of the data points are a little bit sparse. So I did look at the effects of uncertainty and sort of how we were predicting the antivenoms and the neutralised venom to move. So basically, to do this, I actually repeated the global simulation set, except for kind of each antivenom scaffold. I basically incorporated a random twofold scaling factor to each one of the predictive parameters. So this was for the neutralised venom complexes and also the antivenoms. And then I basically redid the global simulation set, and then we repeated the parameter optimization and the global sensitivity analysis. And the results of this basically have shown that the sensitivity profiles are actually really, really similar. There's a little bit of difference, but it's very, very similar when you include this uncertainty. And in addition to that, the kind of parameter space of optimized antivenoms is also actually quite similar. So yeah, I definitely think hopefully in the future there'll be more kind of data on these scaffolds, and ideally in the future you would do kind of like a standardized assessment of different scaffolds, and particularly as well these like next generation scaffolds. But for this model in its like current form, like uncertainty across those parameters and those parameter predictions doesn't really seem to like impact the overall kind of functioning of the system and sort of the suggestions for what an optimized antivenom looks like.
In your simulations, it showed that the two different venom types had very different behaviors in terms of, I guess it's kaon and timing. Can you talk a bit about why you think that's so?
Do you mean, sorry, can you repeat the question? Do you mean the venoms with the kaon? Do you mean the venoms or the antivenoms with kaon and timing?
I think they mean that there was a smaller group of tolerated kaons for the one antivenom.
Okay, yeah. So I think it's about the viper envenomation case basically having a narrower area of parameter space. It's a really good question. I'm not entirely sure. I suspect it's possibly due to the fact that maybe that this venom is essentially like persisting for much longer in the body. Therefore, it's probably advantageous that you've got something that's going to kind of neutralize it and hold on for like as long as possible. Because, you know, the thing as well is like if you've already got like a large toxin, at the point at which it's kind of bound by another toxin, it's actually only going to kind of slow down its motion through the body. So that's potentially something that's going on. But yeah, I myself am not entirely sure why it's that much more stringent, because I mean, yeah, the venoms, we dose them the same. They've actually got quite similar bioavailabilities. Yeah, I would anticipate it's probably to do with sort of like the half-life and just, yeah, I'd anticipate it's to do with the half-life, because the thing as well is, so like the kaon, we found that kaon was more important, which is, it's a little bit unusual, I think, because it's commonly kind of suggested that kind of like KOF is more significant just because that determines your occupancy time. But I think basically the dynamics that we see in this model is that because we consider the rebinding, your K-on is effectively also increasing occupancy time, because if you unbind, you can immediately rebind if the count's high enough. So maybe I would imagine that was kind of probably what was going on there, that it's increasing occupancy time, which is better if it's a longer lasting venom.
Great. Thank you so much. We are out of time, but this has been an absolutely fascinating and very, very nice webinar, Natalie. I am so glad you decided to give us a try and present. And I learned an awful lot about not just snake venom and antivenom, but about antibodies and binding and unbinding of antibodies. So
Yeah,
great
thank
work.
you. Thank you. Yeah, thank you. Yeah, thanks so much for having me. And yeah, thank you so much for everyone who's tuned in and asked questions. Yeah, really, really appreciate it. Thank you.
And I hope everybody in our audience will come back again for a future webinar. And let's give a great hand for Natalie. And thank you, Natalie.
Thank you. Thanks.
Goodbye, everyone.